So imagine you're driving a really high-performance electric vehicle down this massive, incredibly long mountain
Oh,
pass.
yeah, like a really steep winding grade where you're just riding the brakes.
Right, exactly. But you aren't really using the friction brakes, right? You're heavily utilizing regenerative braking. So the vehicle's kinetic energy is being taken by the traction inverter, converted back into direct current, and just pouring massive amounts of energy right back into the high voltage battery pack.
Which is a ton of stress on the system, even if you don't feel it.
Yeah. Because from the driver's seat, the deceleration feels perfectly linear, you know? The software makes it feel completely seamless.
Yeah.
But beneath the floorboards, inside that sealed metal box, the chemistry of the lithium-ion cells is being pushed to, like, its absolute physical limit.
The electrochemistry is essentially redlining.
Exactly. You've got ions racing across separators, squeezing into the anode matrix, and it brings up this fundamental engineering problem. What actually physically prevents that localized electrochemistry from just exceeding its thermal and voltage limits during that sustained surge? Like,
Yeah.
what keeps a single cell from going into thermal runaway right there on the mountain?
Well, the short answer is uh, a terrifyingly complex safety net,
Yeah,
because the margin for error in that specific scenario is effectively zero.
zero margin.
Basically zero, yeah. I mean, we are talking about storing immense amounts of chemical energy in a very tight volumetric footprint.
Right.
If the internal algorithms, or even just the physical shunting hardware, miscalculate that cell's ability to accept the regenerative current by even like a fraction of a volt,
Things go bad quickly.
very quickly, the electrolyte starts to decompose. You get gas generation, massive internal pressure spikes, and ultimately a catastrophic venting event. Fire, essentially.
Which brings us perfectly to the core focus of our deep dive today, because we are pulling from a highly dense stack of automotive engineering manuals, internal testing protocols, battery pathology reports, all to unpack this very specific critical diagnostic protocol.
The infamous P0DE7 code.
Yes, P0DE7. For the engineers out there, this specifically governs the system high voltage execution and global safety layer. It deals directly with single cell overvoltage and what they call passive balancing open circuit failures.
Right, and our mission today is to essentially trace this architecture across 5 distinct engineering dimensions.
Right, going from the root cause of the failure all the way through the software and hardware defenses, the theoretical design protections, the manufacturing controls, and finally how they basically torture test it in mass production validation.
Because P0DE7 isn't just, a superficial check engine light. It's the absolute front line of the battery's safety architecture. We're examining deeply embedded physical fail-safes.
Okay, let's unpack this. Let's start with the baseline architecture, that first dimension, right? The root cause. To understand why a POVDE7 fault even happens, we have to talk about passive balancing.
Yeah, the passive balancing circuit is key here.
So if a battery pack is like a choir, passive balancing is kind of the conductor making sure no single cell sings too loudly, right? Because in a series connected pack, you have hundreds of these cells.
Hundreds of them, yeah. And due to just basic manufacturing tolerances like variance in internal impedance or slight differences in the active material coating, they don't all behave exactly the same.
Right, or even just thermal differences across the pack itself.
Exactly. So they charge and discharge at slightly different rates. Over time, their state of charge just sort of drifts apart.
And to fix that, the passive balancing circuit uses an N-channel MOSFET in series with a power resistor wired across every single cell. So when the battery management system, the BMS, sees a cell's voltage creeping higher than the rest, it basically flips that MOSFET switch.
It drives the gate high, yeah. And that bypasses a portion of the charging current through the resistor. So it burns off that excess electrical energy as heat, joule heating.
But the stress on that tiny circuit is insane.
Yeah. It's immense. I mean, the resistor is converting electrical energy directly into thermal energy inside an environment that is already super constrained thermally.
Which brings us to the actual failure. P0DE7 specifically spots when that bleed circuit breaks down. And the documentation outlines the first major failure mode as the open circuit.
Right, the open circuit, this is when the physical electrical pathway is just severed. So maybe the power resistor suffers a thermal stress fracture, or the MOSFET itself breaks down and fails in the open state.
Meaning it can't close the circuit anymore, it can't bleed the energy.
Exactly. The channel is totally dead. And the really insidious thing about this open circuit failure is that the system doesn't immediately crash.
Right, it's a silent failure at first.
Completely silent. Over, hundreds of charge cycles, this one specific cell can't be top balanced anymore. So its resting voltage slowly drifts higher and higher compared to the rest of the string.
The gap just keeps widening.
Yeah. And the critical vulnerability, the really dangerous moment, is exposed during a high current charging event,
Hmm.
like our mountain pass scenario, or plugging into a massive DC fast charger.
Because the rest of the pack is at a lower state of charge, so the car is still requesting maximum current from the charger.
Right, but this one unbalanced cell is already sitting right at its upper voltage threshold.
Yeah.
So when that surge of current hits, its voltage just spikes dramatically.
And when a ternary lithium cell, like a nickel manganese cobalt chemistry, blows past its upper limit, which is what, like 4.2 or 4.3 volts?
Yeah, right around there, depending on the exact chemistry. When it hits that, the actual structural integrity of the cathode lattice just starts to collapse.
Mm.
It literally releases oxygen, and at the exact same time, the electrolyte is oxidizing against the cathode. So you suddenly have an oxygen-rich, highly reactive environment with intense localized heat.
Which is basically the recipe for a bomb.
It is the fundamental pathology of thermal runaway. Yeah, it's a chemical breakdown triggered entirely by a blind spot in the balancing circuit.
Okay, so that's the open circuit. But what if it fails in the other direction? The documentation calls this the stuck-on state.
Yeah, this is failure mode 2, and it's basically a localized parasitic drain. It happens when the MOSFET gets hit by a voltage spike or maybe gets too hot, and the internal silicon structure actually melts and fuses together.
It just welds itself shut.
Exactly. The drain and source terminals are permanently shorted, so the resistor is just permanently engaged.
Even when the car is off.
Even when it's in deep sleep in your garage, pulling 0 amps from the main contactors, this broken little circuit is just continuously bleeding milliamps of current from that one single cell.
Man, so over a few weeks, that cell just gets dragged down into a severe undervoltage state.
Right, and undervoltage is just as bad, because then the copper current collector on the anode side starts to dissolve into the liquid electrolyte.
Wait, the copper actually dissolves?
It dissolves into ions, yeah. And the terrifying part is what happens next. When the user finally goes to charge the car, those dissolved copper ions precipitate out as solid, metallic copper dendrites.
Like little metal stalagmites.
Exactly. And they pierce right through the separator, causing an immediate hard short circuit inside the cell.
So either way, open circuit or stuck on, you're looking at a catastrophic electrochemical failure.
Yeah. And here's where it gets really interesting. The engineering reports map out this highly specific cascade failure, like a domino effect, showing how fast this goes from a tiny manufacturing defect to a full vehicle fire.
Let's trace that cascade, because the trigger they cite in the case study is wild. It starts with ultrasonic welding, right?
Yeah. When they weld the cell tabs to the bus bars in the factory, a microscopic droplet of molten metal, just weld spatter, gets ejected, and it accidentally pierces the ultra-thin polymer separator inside the cell.
So it creates this tiny localized microshort, not a hard short that instantly explodes, but a highly resistive path between the anode and cathode.
Right. And this induces what the internal diagnostics call dynamic polarization, which essentially means the cell's voltage starts violently fluctuating, diverging really fast from the rest of the pack.
And the BMS sees this, right? It logs an initial, totally separate diagnostic code, P0DE7.
It does, and the BMS tries to fix it. It sees this cell's voltage going crazy, so it commands the passive balancing circuit for that specific cell to engage continuously. It's trying to bleed it down to match the others.
But it's using a component designed for, like, intermittent low-duty cycle voltage shaping and forcing it to run at 100% duty cycle to fight a permanent internal microshort.
Exactly. It's a losing battle. The thermal load on that little balancing resistor massively exceeds its continuous power rating, so the component goes into extreme thermal runaway right on the printed circuit board.
It just violently overheats until the substrate literally cracks. The circuit is destroyed.
And that exact moment of destruction when the channel dies, that is when the P0DE7 code is logged.
The passive balancing is dead, but the dominoes keep falling, right? Because the localized heat on the circuit board has secondary consequences.
Huge consequences. Because to manage the heat of a high-energy pack, they route liquid cooling tubes, usually a water and ethylene glycol mix in incredibly close proximity to these balancing circuits.
Oh no, so the intense radiant heat from the burning resistor
Melts the adjacent cooling tube, yeah.
Wow.
The polymer or thin aluminum tubing just breaches, and it releases that highly conductive coolant directly onto the internal electronics.
And when that liquid bridges the gap between the high-voltage copper bus bars and the grounded chassis?
You lose high-voltage isolation. The coolant acts as a literal bridge for high-voltage arcing, And that localized short circuit on the main power bus triggers the final diagnostic code, P0DE7. Total high voltage isolation failure.
That is horrifying. I mean, in a matter of hours, a microscopic weld spatter forces the primary safety system to destroy itself, melts the thermal management system, and creates a massive high voltage short.
Which leads to an uncontainable vehicle fire. Exactly. This is why a tiny manufacturing defect can be lethal if the overarching architecture isn't totally bulletproof.
Okay, so knowing this terrifying domino effect is possible, how does the vehicle's brain spot that first falling domino and stop it in real time? Which takes us to section 2 of our deep dive, the technical architecture and fail-safes.
Right. So the BMS has to meet ASIL-D standards. That's the automotive safety integrity level, the absolute highest level of safety certification.
Reserved for systems where a failure basically means a fatal risk.
Exactly. To prevent lithium plating, explosion, thermal runaway, it requires a deeply decoupled dual-layered defense system.
So let's talk about layer 1, the software layer.
The main computational brain here is the microcontroller unit, the MCU. It's constantly crunching data from the analog front end, or the AFE. The AFE is the chip physically touching the cell terminals, digitizing the voltages.
And the MCU evaluates that data against super strict thresholds. For a ternary lithium battery, the critical trigger point is exactly 4.25 or 4.26 volts.
Right. And if a cell sustains that voltage, the software has to trigger an overvoltage protection event, an OVP, and physically open the charging relays.
But the timing here is just as crazy as the voltage limit. The specification says it must exceed 4.25 volts for exactly 1.68 seconds before triggering the OVP. Why 1.68 seconds exactly? Why not instantly?
That is a highly calibrated debouncing filter. Think about the electrical noise inside an EV. You've got the traction inverters, silicon carbide MOSFETs switching at incredibly high frequencies.
Right, chopping up the DC into AC for the motors.
Exactly. And that generates massive electromagnetic interference, EMI. This EMI can actually induce fake transient voltage spikes on the AFE sensing lines that last for microseconds.
So if the software reacted instantly to every fake spike?
The car would just violently shut off every time you accelerated or braked. It would be undrivable. So a 1.68-second window lets the algorithm filter out the inverter noise. It confirms the overvoltage is a real chemical reality, not a phantom EMI ghost.
It calculates the actual true battery voltage rise against the high frequency noise. That is brilliant. But wait, let me push back on this for a second. If the software is already monitoring everything in real time and it's this sophisticated, why do we need a separate hardware system? Isn't the software fast enough?
Well, relying only on the MCU is a massive vulnerability.
Yeah.
We're trusting a microprocessor running a massive real-time operating system to stop a bomb from going off.
And software crashes.
Software crashes. You could have a memory leak, an infinite loop, a task scheduling conflict. If the MCU lags for even 50 milliseconds, right as a cell hits the thermo runaway point, your software layer is completely useless.
Oh, man. So that introduces layer 2, the hardware layer.
This is the concept of hardware decoupling. You can't get ASIL-D certification if a single software glitch can kill your safety mechanism. So layer 2 lives entirely inside the analog hardware domain.
Inside the AFE chip itself.
Right. Completely isolated from the main MCU data bus. It has a dedicated hardware comparator circuit. It uses a deeply stable internal reference voltage that doesn't drift, even if the pack gets super hot.
And it just compares the raw, undigitized cell voltage straight against that hardwired limit.
No code, no scheduling priorities. It's a pure physical logic gate. If the raw voltage breaches the physical threshold, it acts totally autonomously. It bypasses the software entirely using a dedicated line called the fault pin.
So while the MCU is, sending a polite software request over the data bus to open the relays, the hardware comparator just physically cuts the control voltage to the relays via that fault pin.
Exactly. It's the difference between clicking shut down on your computer menu versus just yanking the power cord out of the wall.
That's a great analogy. It guarantees a mechanical disconnect no matter what the software is doing. But this dual-layer setup does more than just emergency cutoffs, right? It actively diagnoses itself.
Yeah, the internal documents call these the diag routines. The car doesn't just sit around waiting for a 4.25-volt emergency to see if its safety circuits are working. It actively probes them.
Like when the car is asleep.
Right. During sleep mode, the AFE briefly wakes up the sensing circuits in the dead of night. It runs a high-precision voltage sweep to look for any tiny, weird voltage drops across the cells.
So it's looking for that stuck-on MOSFET failure we talked about, the parasitic drain.
Exactly. If a channel fuse closed and is secretly draining a cell, The hardware spots that microcurrent draw while you're sleeping and throws the P0DE7 code before the cell gets destroyed by undervoltage.
And during active charging, it shifts to testing the dynamic leakage current, injecting a test current, measuring the voltage drop, making sure the resistance isn't infinite.
Which would confirm the open circuit failure.
Yeah.
It is constantly mapping the health of every single balancing component.
Okay, so let's go back to our mountain pass scenario from the intro. If the pack gets too full on that downhill run, how does the system prevent the overvoltage without just violently yanking the power cord and making you lose your regenerative braking?
That's where dynamic derating comes in. Instead of waiting for the hardware comparator to violently sever the high voltage contactors, which, like you said, would instantly drop your braking torque and terrify the driver, the MCU recalculates the state of power, the SOP.
It actively limits the maximum allowed charging current.
Right? As that leading cell gets close to the limit, the MCU broadcasts a reduced regenerative torque limit to the vehicle control unit, the VCU.
And the VCU talks to the mechanical brakes.
Seamlessly. It mathematically blends out the electrical regen torque and blends in the hydraulic friction brakes via the ABS module.
So for the driver, the deceleration curve is completely smooth. You don't even know it's happening. But the energy dissipation is transferred from the battery chemistry to the brake rotors,
Entirely mitigating the risk. It is a total masterclass in software state management.
Real-time digital defenses are amazing. But what if we can design the hardware so that the physical components inherently protect themselves before the software or the hardware comparators even have to intervene? Which brings us to Section 3. DFMEA, designing for the worst case.
DFMEA, Design Failure Mode and Effects Analysis. It is an exercise in applied pessimism.
I love that phrase, applied pessimism.
I mean, they literally model the absolute worst-case operational environments because the risk of thermal runaway from an overcharge event is rated a severity 9 out of 10. A severity 9 means catastrophic failure with potential loss of life and absolutely zero advanced warning to the vehicle occupants.
So because it's a severity 9, the protections have to be fundamentally passive, like physically infallible.
Right. And what's fascinating here is how they use worst-case circuit analysis, or WCCA. They run these massive Monte Carlo simulations, injecting the maximum possible tolerance stack-ups for every single resistor, capacitor, semiconductor on the board.
And they assume the board is operating in an 85 degrees Celsius environment, which is like a desert fast charge in the middle of summer.
Exactly. They calculate the thermal derating margins to prove that the normal heat from the balancing resistors won't melt the actual FR4 fiberglass circuit board.
But WCCA also means designing for things going wrong. So they assume the MOSFET gets a static shock and gets stuck on, forcing the resistor to dissipate max power continuously in that 85-degree environment.
And this is where the genius of the design comes in. To stop that cascade failure, where the board carbonizes and melts the cooling tube, they put independent microthermal fuses on every single balancing circuit.
The PTC fuses.
Yes, positive temperature coefficient devices. They are incredible. It's a crystalline organic polymer matrix loaded with conductive carbon black particles.
So at normal temperatures, the polymer is dense, the carbon particles touch each other, and current flows normally.
But when that resistor goes into thermal runaway because of a stuck MOSFET, the radiant heat hits that PTC fuse. And when it hits a specific temperature threshold,
The physics of the polymer completely change. It expands.
rapidly, it goes from crystalline to an amorphous expanded state. And as it volumetrically expands, it literally pulls the conductive carbon particles apart from each other.
The conductive chains are physically severed.
Instantly. The electrical resistance skyrockets by orders of magnitude in milliseconds. It effectively chokes off the current flow, physically breaking the circuit through thermomechanical expansion.
So the runaway heat is stopped before it can melt the board or the cooling tubes. The channel dies, the P0DE7 fault is logged, but the massive thermal cascade is completely neutralized.
And it requires zero software, just the intrinsic physics of the polymer.
That is so cool. And the DFMEA protections go even deeper, right? Down into the actual battery cell itself. We talked about that microscopic metal weld spatter piercing the separator earlier.
Right, the trigger for the microshort. To fundamentally eliminate that root cause, engineers actually armor the separator.
Standard separators are just thin plastic films, right? Like polyethylene.
Yeah, microporous polyolefin films. But they are really weak to thermal shrinkage and mechanical punctures, so the design mandates a ceramic coating directly onto the polymer film.
Aluminum oxide, Al2O3.
Exactly. They mix these aluminum oxide nanoparticles with a binder and coat the side of the separator facing the cathode. It massively increases the mechanical tensile strength.
So when that high-velocity metal spatter from the welding process impacts the separator, it hits the ceramic armor. The mechanical energy is dissipated, and it can't penetrate the plastic film underneath.
The microshort is never established. The dynamic polarization never happens. The BMS never overdrives the circuit. The resistor never overheats. You eliminate a massive percentage of the P0DE7 failure tree before the pack even leaves the factory.
Which is an incredible theoretical design, microfuses, ceramic armor, but a design is only a piece of paper until it's built.
Right.
And ironically, the process of building these safety systems can actually damage them. Which brings us to the factory floor. Section 4, PFMEA, Process Failure Mode and Effects Analysis.
The factory floor is incredibly hostile to high-voltage surface mount technology. The SMT soldering process itself is a major thermal threat.
Right, because to solder the board, it goes through a massive reflow oven to melt the paste. And the thermal dynamics are tricky. The power resistors and MOSFETs have a much larger thermal mass than the tiny microcontrollers next to them.
Which creates a huge problem. If the reflow oven temperature profile, the TCT, isn't perfect, you get severe thermal gradients across the board. The printed circuit board and the ceramic substrate of the thick film resistors have totally different coefficients of thermal expansion, CTE.
So if they cool down too fast, they contract at different rates.
Exactly. The FR4 board shrinks differently than the ceramic resistor. And that CTE mismatch generates immense shear stress at the solder joints, which propagates right into the ceramic substrate,
Creating microscopic stress fractures.
which might pass the initial factory test.
Right, they definitely will pass. But it's a delayed action failure. You put that car on the road, subject it to high-frequency vibration from potholes, thermal cycling from fast charging, and over 3 years, those microcracks grow.
Until the ceramic substrate shears completely in half.
The circuit is physically severed. A P0DE7 open circuit failure caused entirely by a poorly calibrated cooling fan in an oven 3 years ago. Wow. So they have to dynamically monitor the oven profiles constantly. But that's just the heat. The factory also has invisible threats, like static electricity.
ESD, electrostatic discharge. It is an assassin on the assembly line. You've got robotic arms, conveyors, technicians moving around. They constantly generate triboelectric charge.
And the internal gate oxide in these MOSFETs is, what, nanometers thin?
Incredibly thin. An ESD strike of even a few hundred volts, which you wouldn't even feel if it shocked your finger, will cause avalanche breakdown in the MOSFET. It melts the silicon, punctures the oxide, and fuses the drain and source together.
Boom. The stuck-on failure mode is born right there on the line.
Exactly. So standard grounding wrist straps aren't enough for ASIL-D. They deploy dynamic electrostatic impedance monitors everywhere. If the static field in the air gets too high, it automatically triggers overhead ionization blowers to flood the area with positive and negative ions, neutralizing the charge.
It's like a sci-fi clean room.
It has to be.
And then, once it survives the oven and the static, it has to be sealed. Because of electrochemical migration, ECM.
Moisture is the final enemy. Even inside a sealed battery pack, constant heating and cooling means any trapped humidity will eventually condense right on the circuit boards.
And if a micro droplet of water bridges the gap between two high-voltage pins on the AFE chip, it creates a microscopic electrolytic cell.
The water acts as the electrolyte. The metal from the anode pin, the copper or silver in the solder, starts to dissolve. The ions migrate across the water to the cathode pin and resolidify.
Creating those dendrites we talked about earlier.
Right. They grow across the surface of the board until they bridge the gap entirely, creating a permanent, hard short circuit between the ASIL-D sensing lines.
So how do they stop that? Imagine trying to vacuum seal an entire city grid to prevent flood damage. They use a conformal coating, right? The documentation calls it a 3-proof paint.
Yeah, usually a highly engineered polyurethane or acrylic resin, but they can't just spray it on, they apply it under vacuum.
To suck out all the microscopic air bubbles from under the chips.
Exactly. Because an air bubble can trap moisture or expand during thermal cycling and crack the coating. Once the vacuum process is done, automated 3D laser vision systems scan the whole board to verify the exact micron thickness of the resin over every single solder joint.
An impenetrable dielectric barrier. No water, no electrochemistry, no short circuits.
And then, before it even goes into the pack, it hits the end-of-line testing, the EOL. Automated machines force every single passive balancing channel to activate under load.
They measure the exact dynamic voltage drop across each MOSFET to guarantee there are no fake cold solder joints, no stuck open faults, no fuse shut channels.
Absolute zero out-of-the-box hardware faults allowed.
Okay, so the factory says the process is perfect, the engineers say the design is perfect, but car manufacturers don't just take their word for it, do they?
Oh, absolutely not.
They torture test it, which brings us to the fifth and final dimension, the DVP&R. The Design Verification Plan and Report. This is mass production validation testing.
This is where they mathematically prove that the entire P0DE7 architecture will operate with absolute determinism for at least 10 years or 300,000 kilometers.
And they test the timing first, right? The 1.68-second FTTI race, fault-tolerant time interval.
Right. They put the BMS on a massive hardware-in-the-loop supercomputer simulator at each aisle rig. It faked the entire car, the inverter harmonics, the CAN bus traffic, the dynamic cell voltages at maximum load.
And while the MCU is sweating under all that fake data, the engineers act like saboteurs. They inject a massive instantaneous 4.30-volt analog signal directly into the AFE chip.
A simulated catastrophic overvoltage event with zero warning. And the hardware comparator has to spot it in microseconds, pull the physical fault pin low.
While the software is simultaneously racing to filter the noise, confirm the voltage for the 1.68 seconds, and log the P0DE7 code to memory.
But the only metric that matters is the total response time to mechanically sever the high-voltage contactors. From the microsecond that fake voltage hits to the microsecond the relays snap open and current hits zero. It must be rigidly less than or equal to 1.68 seconds plus the mechanical relay latency.
If the operating system stutters for a microsecond or the relay coil is sluggish, fail. No delays allowed.
Perfection under maximum load.
Then they do fault injection, the BDS validation, built-in self-test, where they literally take a scalpel and snip wires on the board to simulate an open circuit.
Or use a micro welder to permanently short the MOSFET to fake a stuck-on state.
They mutilate the board, power it up, and the system has exactly 100 milliseconds to spot the sabotage during its self-check.
It has to 100% accurately localize which channel was destroyed, and then it must instantly execute a software downgrade.
Right. It artificially caps the max allowed state of charge for the whole battery pack below 50%, having the energy density so the cells never reach a volatile voltage.
And it permanently locks that P0DE7 code into the non-volatile memory, the NVM. So even if a technician tries to clear the codes with a scan tool or you disconnect the 12-volt battery, the system reads the NVM on reboot and maintains that 50% lock.
You cannot override it and charge a dangerous battery. Brilliant. And then we get to the environmental torture chamber.
The high-temperature forced failure test.
The 85 degrees Celsius oven of doom.
Exactly. They put the functional board in the oven, connect to the debug port, and force the MOSFET to be permanently stuck on.
So it's generating massive joule heating in an oven that's already 85 degrees, and they just watch it with thermal cameras.
They're watching to see if the PTC microfuse does its job. The polymer has to expand, sever the carbon chains, and choke off the current rapidly enough that the absolute maximum temperature on the board never exceeds 120 degrees Celsius.
If it hits 121 degrees, fail. No carbonization, no melting, no fire allowed.
The hardware has to contain its own destruction perfectly.
And finally, the swamp test. The dual 85 ECM test.
This one is just brutal.
They take the coated board and they drop a bead of ethylene glycol coolant right onto the sensitive high-voltage pins,
simulating the worst-case cooling tube leak.
Then they throw it into a chamber at 85 degrees Celsius with 95% relative humidity. It's literally a boiling swamp. And they blast it with a continuous 5-volt bias across those wet pins for 500 agonizing hours.
Which mathematically equates to over a decade of real-world environmental stress.
And after 500 hours, what are the survival numbers?
Leakage current must stay under 1.0 milliamp. Insulation resistance must stay above 500 megaohms. And when they look at it under an electron microscope, there must be 0 microscopic metal dissolution, 0 conductive tin whiskers, 0 dendrites.
Total perfection after 500 hours in a boiling swamp. That is unbelievable. So what does this all mean? We've gone from a tiny metal splash causing a chain reaction of fire to dual-wielding software and hardware defenses to microfuses melting to save the day to vacuum-sealed circuit boards surviving a humidity torture chamber.
It means that the next time you plug in your EV or use regenerative braking down a hill, you should picture these ASIL-D protocols working in microseconds.
Right.
This vast, invisible architecture exists entirely to ensure the energy powering your life remains perfectly contained.
It really changes how you look at the car in your driveway.
It does, but, as battery chemistries continue to evolve, say, with the advent of solid-state batteries that are theoretically immune to thermal runaway because they don't have liquid electrolytes,
All right.
it raises a fascinating question. Will these elaborate physical hardware defenses, like melting PTC fuses and ceramic armor, become relics of the past? Or will the sheer raw physics of storing immense amounts of gigajoule energy always demand a physical analog kill switch, no matter how smart our AI software becomes?
Wow. Can software ever truly replace the deterministic safety of a physical kill switch? That is something to chew on. Thank you so much for joining us on this incredibly detailed deep dive into the hidden complexities of the P0DE7 protocol. See you next time.